Hello. Hope you're enjoying the Mardi Gras break, if it is a break at all. It's not for me. It's Monday of a break, and here I am, and to an empty classroom, and now I'm going to cover the rest of Chapter 4. I would recommend going through this video before you do the homework and quiz related to Chapter 4, so that hopefully things will be a little clearer. So I have no idea how long this is going to take. Hopefully not terribly long, but I do have several pages of notes to get through. So let's just see what happens. Okay. Now, first, going by the sections in the book, 4.4, the singular value decomposition. Also known as the SVD. Okay. In spite of all my exposure to linear algebra as an undergrad, I had not heard of the SVD until I was a graduate student at Stanford. And one cannot pass through Stanford in a mathematical setting at Stanford without hearing about the SVD, because it was my advisor there, Gene Golub, who developed the first practical algorithm for computing it back in the year I was born, 1969. It was probably the the most singular achievement of his career, in a career that had a great many achievements. But it's what he was best known for. I'm actually not going to talk about the algorithm for computing the SVD today. Now the SVD, as I'll write out later, is another matrix factorization. But compared to other factorizations we've seen so far, like the LU decomposition or the Cholesky factorization or even the QR factorization, it is one that cannot be computed by an algorithm that terminates in a finite number of steps. It requires an iterative method. So once we cover methods for computing eigenvalues, which will happen later on when we get to Chapter 6, then I'll be able to present this algorithm. But what I'm going to show you is prove its existence and give the many important properties that it has. But yeah, the SVD and Gene Golub go together so closely that his license plate was Prof. SVD, and for his 60th birthday, the cake was decorated with the entries of a matrix, where if you computed the singular values of a matrix and mapped them to characters using ASCII character codes, it spelled out "Happy Birthday, Gene." So I feel bad for the cake decorator on that one. Okay, so the singular value decomposition has a lot of applications, but it's decomposition is particularly useful for various least squares problems, which is why it's included in this chapter. Okay, so what I'm going to do is, this applies to any matrix. I'll stick with any real n by n matrix, and I'm not going to make any assumptions here about the rank of A or even the dimensions of A. And in this chapter, we've assumed that m is greater than n. But any matrix whatsoever has a singular value decomposition. So we're just going to keep it general for now. Except for the fact that it's real, I'm not going to talk about the complex case because it doesn't really add in anything interesting this time. Now, I'm going to, the singular value decomposition is tied very closely to the matrix 2 norm. And you're going to see the extent of that connection as I go through this. But it also plays a role in actually proving that the SVD actually exists for any matrix. So I'm going to recall that the 2 norm of a matrix is equal to the maximum over all vectors. So in this case, it would be n vectors, where the vector 2 norm is equal to 1. So all vectors with a Euclidean length of an n-dimensional space of 1. The maximum of the vector 2 norm of a times x. So you have a unit vector. The 2 norm is the greatest extent to which the Euclidean length of a vector can be amplified through multiplication by a. And this maximum definitely exists. This is a set of all unit vectors as a compact set. So this function, if you will, of taking the norm of a times x has a definitive maximum and a minimum on this set. So I'm going to define sigma, Greek letter sigma, to be the matrix 2 norm of A, whatever it might be. It's going to be some non-negative number. Well, it's going to be positive unless the matrix itself is 0. I'm going to choose to find a vector, or I'm going to label a vector by x. So x, which is n vector, be a vector such that if you it has these properties. First, I'm going to stipulate that it is a unit vector. So there is some unit vector where if I compute a times x and take its vector 2 norm, the result is going to be the 2 norm of A, sigma. So there has to be some vector x that's a unit vector such that the norm of A times x is equal to the 2 norm of A, which is sigma. All right, so in other words, it's a vector I can multiply A by, but actually brings about the maximum value of this. Okay. Now, more notation. I'm going to let z be equal to A times x. And I'm going to define y as the normalization of z. I'm going to divide z by its 2 norm. So that way, y is also a unit vector. So this is in Rm. So what that means is A times x, which is z. But now I can write this as, by using this relationship between y and z, I can write it as 2 norm of z times y. But the 2 norm of z is, z is ax. So the 2 norm of z is a 2 norm of ax, which is sigma. So, all right, so ax is equal to sigma y. So that's a relationship that I'm going to need. Okay. And the reason I'm doing this normalization, to remind you, that makes y unit vector. So, so to recap, I have ax is sigma y, and both x and y are unit vectors in their respective spaces. Okay. Now, what I'm going to do is make use of householder reflections. So I can define U1 and V1. Be householder reflections. So V1 is n by n matrix, and it's chosen so that V1 times x is equal to E1. Now, when I covered householder reflections from QR factorization, what happened was we were given some vector that may have been like a column of A, for instance, or part of a column of A, and we figured out how to make a householder reflection that, when multiplied by that vector, gives you a multiple of E1, plus or minus. Now, in this case, this is why it's very important that I stipulate up front x is a unit vector, so that this can be a unit vector also. Because V1, the householder reflection, is an orthogonal matrix. When you multiply it by a vector, it cannot change the length of the vector. But since this is a unit vector, now I know this is too. Okay, so this is the magical householder reflection, but it's not magic because I showed you before how to make it. It zeroes out all the entries of x except for the first one. And then U1 will be defined in a similar way. U1 is an m by m matrix, so that if I apply it to y, I also get E1. All right. Now, what I want to look at is what does this matrix, U1 transpose A V1, what does this matrix look like? Okay. What structure does it have? Okay, so what I'm going to do is, I'm really only interested in its first row and its first column. So I'll start with the first column. Now, how do you get the first column of a matrix? You multiply by E1, first column of identity. So U1 transpose A, V1, E1. Okay. Now, I want to recall something about householder reflections. What was shown was the householder reflection is its own inverse. So here I have V1x is equal to E1, and similar for U1. So I'm going to write out what it means. The fact that it's its own inverse, that means that V1 E1 is equal to x. U1 E1 is equal to y. So I can put V1 here or here. And the equation is correct because it's its own inverse. So in other words, I can multiply both sides of this by V1. V1 goes over here. V1 times V1 is its own inverse, so it becomes identity over here. And that's how you get this. Okay, so I can use this relationship over here. V1 E1 is equal to x. Transpose AX. Okay. Now AX is sigma y. Now, sigma is just a number. I can pull it out. So that's sigma U1 transpose y. Okay. Now, what else do we know about household reflections? Now, if you're all here, I would just wait for you to answer. But I guess, hopefully, for you not being here, I can move things along faster. It's symmetric. So it's a sigma U1 y, but U1 y is E1. So I get sigma E1. So the first column of this matrix that I'm interested in, we now know that that first column is all zeros except for the first entry, which is equal to sigma. All right. Now, that's the first column. Let's take a look at the first row. Okay, so that's going to be, I'm going to multiply on the left. So how do you get a row of a matrix? You multiply by a row of identity on the left. So I want the first row, so that's E1 transpose, U1 transpose AV1. Okay. Now, using the fact that the product of transposes is the transpose of a product in reverse order, so that would be U1 E1 transpose AV1. Now, U1 E1, I have that over here. That's Y. So Y transpose AV1. Now, I'm going to write that. If I write this as A transpose transpose, then I can write this as A transpose Y transpose V1. Again, using a property that the transpose of a product is a product of transposes in reverse order. Okay. So, unfortunately, I did not get as far. And I was able to get a firm handle on what the first column of this matrix is, but I don't really know anything more about the first row than when I started, because I don't know anything about A transpose Y. So we need to gather some information about that. Okay, so drives me nuts. In the room, the tables getting choked. I swear that all of you students, no matter what class you're in, who your instructor is, like you're trying to box them in at the front of the room. I gotta say, kind of creepy. Okay. Okay. We actually not have to contend with a glare zone. Well, it may be unavoidable. There's nobody here who's going to keep moving its back. Okay. Oh man, why did I do this? Okay. Well, I'm going from a book here. Earlier I used Z to refer to A times X. And then I reuse that letter to refer to A transpose Y. It's not really incorrect, but could cause confusion. But I'm going to stick with what's in the book. And besides, the previous Z, A times X, I no longer have need of it. So it's not going to lead to anything wrong. Okay. So, whoever comes in here for first class tomorrow is going to find this room in disarray. So, well, not tomorrow, Wednesday. Okay. All right, so I'm going to let, too many chairs back here. So my new meaning of Z is A transpose Y. Okay, so forget about the old Z. Besides, students have to keep in mind that once you assign a letter to a symbol, it's not bound to that symbol for all time, because otherwise you run out of letters very quickly. Okay, now, any vector can be written as a unique linear combination of vectors that are orthogonal to one another. So now, actually, I don't even need orthogonality. If you have a set of vectors that are linearly independent, then any vector that's a combination of them can be written as a unique linear combination of them. That's what linear independence means. So orthogonals is a stronger form of linear independence that gives you other nice properties. So I can write z as a constant times x plus another constant times a vector w, where I don't know anything about w except it's orthogonal to x. Okay. All right. And I'm also going to specify that w is a unit vector, just like x is. And I can do that because it's multiplied by some constant d I don't know anything about. So I can always scale this term so that w is a unit vector, and then whatever magnitude it might have had just goes into d. All right. So now what I'm going to do is I'm going to take the dot product or inner product of z with x. So that would be equal to, so I take both dot product of this with x, so I get c x transpose x plus d x transpose w. Now, dot product of real vectors is commutative, so x transpose w, that's 0. And x is a unit vector, so the dot product of x with itself is 1. So this dot product of x transpose z is just c. Okay. Oh boy. Okay, wait. Let me make sure I didn't mess this up. It might have gotten in conflict with maybe 2 meanings of z after all. I sure hope not. Well, I'm already fixing mistakes in the book anyway. I found 2 more preparing this lecture. Okay. Well, I'm just going to keep working this and see what happens. Now, I can keep in mind how I defined z. Z is A transpose Y. Okay. Now, here again, I have a product of transposes, but that's the same as the. Now keep in mind that this is. Well, actually, I'm going to back up a little bit. I've just established this is equal to C. So C is equal to X transpose Z. And then I'll fill in what this Z is. Okay, A transpose Y. Okay, here I use the fact that the product of transposes is a transpose, transpose of a product as long in reverse order. So this would be AX transpose Y. Okay. Now, AX, okay. To conclude, there's not a mistake in the book. Thank goodness. Again, just an unfortunate choice of notation. Because we know what AX is from before. AX is sigma Y. So now I have sigma Y transpose Y, but Y is a unit vector. So Y transpose Y is equal to 1. So in other words, C equals sigma. So now I can say that Z, which is A transpose Y, is equal to sigma X plus this other term here, D times W. Okay. Now, X and W, as I mentioned, are orthogonal to one another. And here's how that's helpful. I'm going to write out a property of inner products that is often useful. just use generic vectors I can use anywhere else. If I have the 2 norms squared of a sum of vectors, A and B, well, that's the, and I may have done this before, but repetition doesn't hurt. That's the same as the dot product of A plus B with itself. So if I FOIL this, I get A transpose A plus 2A transpose B. Now, for a case where A and B are real vectors, so the dot product is commutative, so I actually can combine the cross terms. I actually get B transpose A and A transpose B, but if they're real, they're equal. Otherwise, they're complex conjugates to each other. Then I get B transpose B. So that, now remember, there are a lot of things I'm using here, little properties that need to be like burned in your brains, like second nature, just like, I don't know, quadratic formula someday. So that's the 2 norm of A squared plus 2A transpose B, so the dot product of A and B, and then plus the 2 norm of B. Now, that's for any real vectors. What if the vectors A and B are orthogonal? Then the 2 norms squared of the sum is the sum of the 2 norms squared. So that's what I'm going to use here with A transpose Y. So using the fact that X and W, which I assumed from the get-go, are orthogonal, the 2 norm of A transpose Y squared is equal to the 2 norm of this term, which is just sigma squared, 2 norm squared, and then the 2 norm of this term. Well, W is a unit vector, so the 2 norm of this term is D squared. Okay. Now, I have an exploration here in the book, which I'm not going to take the time to prove. It would actually, to really prove it, I'd have to do one of your homework problems. So I have been known to give away the answers to homework problems in class in the past, and I'm trying to be better about that. So I'm not going to prove this, but the thing is, I'm going to use a property that's the 2 norm of A transpose is equal to the 2 norm of A. Now, here we have a situation where I'm taking a unit vector y, multiplying it by A transpose. That cannot amplify y by a factor greater than sigma, because sigma is a 2 norm of A transpose as well as that of A. So if I have a situation where I take a unit vector and I'm amplifying it by multiplying it by A transpose to get magnitude of this, that magnitude cannot be greater than sigma. So in other words, the magnitude squared cannot be greater than sigma squared. Therefore, the only conclusion I can draw from this is that D must be 0. All right, so that was, so all of that was just to show that D is 0. So putting this together with something I showed earlier, I have the following. I have AX is equal to sigma Y, and A transpose Y is equal to sigma X. Okay. So now I can go ahead and use that, and it looks like, yeah, barely stayed out of the glare zone. Now I can use that to get a better handle on this matrix I had earlier, U1 transpose A V1. Where's the eraser? The eraser is missing. Okay. All right, I have an eraser here. Okay, so to recap, I'm going to give this a name. A tilde transpose AV1. And as I will have everything in one place. So the first column of this matrix as shown earlier is sigma 1 E1. Now I was working on the first row before I had to go to the other board and work some things out. So the first row okay, so where I got into before was A transpose Y V1, or A transpose Y transpose V1. But now I know that A transpose Y is sigma X. So now I can fill that in. Now, V1 is symmetric, being a household reflection. So I could just put a transpose there just for fun. Well, it's not just for fun because I actually need it. So it's sigma V1X transpose. But V1X, how it's defined, okay, have it right here, V1X is equal to E1. So now I have sigma E1 transpose. So what do we have? The first row of A tilde, this matrix here, I should have written it that way, is all zeros except for sigma in the first position. First row of this matrix, which is A tilde, is also all zeros except for sigma in the first position. So A tilde, which is U1 transpose A V1, has this structure. Sigma in the 1, 1 position, 0 vector down here in the rest of the first column, 0 vector up here. Now I'm going to put a 0 transpose, which is kind of odd, but we treat all vectors as column vectors. So, and here is a row vector. And then I have some matrix down here, which I don't know anything about, call it A1. So A1 is m minus 1 by n minus 1. So after you take this matrix, which is m by n, you just remove the first row and first column, and A1 is left over. Okay. So by finding the vector x, so that AX has a unit vector x, so that AX has the magnitude of AX is the 2 norm of A, the matrix 2 norm of A. And then using householder reflections based on that, I can transform A, using these household reflections, into a matrix where I've zeroed out most of the first row and column. I've been able to separate sigma from everything else. So then what I could do is I could repeat this process on A1. If I could find a vector, so a vector of length n minus 1, that I can multiply A1 by, so that the magnitude of A1 times that unit vector is equal to the matrix 2 norm of A1, then I can zero out most of its first row and column, and I can just keep going. So the result of this is that by applying household reflections on both sides, I can keep transforming A to gradually reduce it to diagonal form. So I've already started doing that by zeroing out most of the first column and most of the first row. So repeating this process, I can just destroy everything except for the main diagonal. Now there's one other thing I want to show is, before I write down the final result, how A1 relates to A. So, all right. So if I let x be any vector in Rn. Now, I want to keep in mind that the 2 norm of A tilde is equal to the 2 norm of A. It doesn't really follow from this, but I want to make a note of it. And the reason why is A and A tilde are related by multiplying by an orthogonal matrix. So when you multiply a matrix by an orthogonal matrix on the left or right, that preserves the matrix 2 norm. I'm not going to go into why because that's a homework problem. I don't recall if I assigned it, so I'm not taking any chances. But it can be proved using various properties of orthogonal matrices. So I'm going to work with A tilde because it has the same norm as A, but it has a simpler structure. So A tilde x, if I multiply by any vector x, so if I won't put any vector x here, then it's going to look like this. The first element is going to be sigma times x1, whatever x1 is. And then the rest of it's going to be a1 times vector y. So I'm breaking x down into two parts. So the first element here and everything else I'll call y, just to call it something. Okay. Now, what that means is the 2 norm of A tilde x is equal to squared is equal to this first component squared, sigma squared x1 squared, plus the 2 norm of this squared. Okay. Now, what we also know is that this 2 norm squared has to be less than or equal to sigma squared times the norm of x squared. Now, if I write out what this is in terms of the components of x, I get sigma squared x1 squared plus sigma squared 2 norm of y squared. So this right here, where we have equality, has to be less than or equal to this. But these two terms match, so I can cancel them. So what that means is 2 norm of a1y is less than or equal to 2 norm of y. Oh, whoops. That should have been sigma squared, not sigma sub 2 that I wrote earlier. So 2 norm of a1y is less than or equal to sigma times 2 norm of y. But sigma is a 2 norm of a. So what this means is, so in fact, if I were to divide both sides by norm of y, assuming norm of y is non-zero, then what I get is, and then taking the maximum, I get 2 norm of a1 is less than or equal to the 2 norm of a. All right, so that's what I needed to establish here, that if we transform A to wipe out most of the first row and column, and we have this leftover matrix A1 here, the 2 norm of that matrix, the leftover matrix, has to be less than or equal to the 2 norm of the original matrix. Okay. Now, so after carrying this first transformation to wipe out most of the first row and column, like I said, continuing the process, you can whittle away at A until it's reduced to diagonal form. So now I'm going to show you the result of that. This is something that mathematicians often like to say. Continuing this process, and really there's a lot behind that, but it follows from what's been written. And I guess if I were to be completely rigorous about this, would do a proof by induction. But this video will be way too long. I think it's way too long as it is. So what we get is we get U transpose AV. So in other words, I keep applying household reflections on the left and right. So they keep accumulating. And what I get is a diagonal matrix with diagonal entries sigma 1, sigma 2, and so forth, down to sigma p, where p is the minimum of m and n. Now, here I've drawn this matrix to be a tall, thin matrix, so m is greater than n, but it doesn't matter. You get the same decomposition no matter what. Is that however many diagonal entries you can have, which is a minimum of m and n, that's how many of these sigmas that you have. Now, U and V are orthogonal matrices, so I can multiply both sides on the left by U, and I can multiply both sides on the right by V transpose to cancel things out. And what I get is U sigma V transpose. So this is the singular value decomposition. Okay, now, so what do we know about U, sigma, and V transpose? So U is M by M, and it is an orthogonal matrix. So U transpose U is identity, also U transpose is identity, square. V is N by N, also orthogonal. And then sigma is this matrix here. So you have sigma 1, sigma 2, sigma 3, and so forth, as many diagonal entries as you can have based on the dimensions of a matrix. Furthermore, as a result of this, what I showed here, that the 2 norm of A1 is less than or equal to the 2 norm of A2, you have sigma 1 greater than or equal to sigma 2, and so on, all the way down to the last sigma you can have, sigma p. And they're all non-negative. The reason why is, how does sigma come about? Sigma was the 2 norm of A. All of these sigmas are a 2 norm of some matrix. So either A itself or the whittled down matrix that you get after each set of household transformations. And these are called the singular values of A. The smallest singular value is actually the, you can think of this as having a quasi-geometric meaning. It's the distance in the 2 norm sense between A and the nearest singular matrix. In other words, if a small singular value is 0, well, A is singular, so the distance would be 0. But if A is non-singular, as linearly independent columns, a small singular value gives an idea of small singular value gives an idea of how close A is in a 2 norm sense to a singular matrix. So if sigma p is particularly small, in other words, what you can say is that the matrix A is nearly singular. Okay. So one geometric meaning of another geometric meaning for all of the singular values is if you are working in n-dimensional space, so you have your vectors v1, v2 up to vn that are all orthonormal. So they define a n-dimensional orthonormal frame. Then if you multiply all those vectors by A, because all of those vectors, since they're orthonormal, they're all unit vectors. So you can think of them as defining an n-dimensional sphere. But what happens is, if you multiply all those vectors by A, you get a new orthonormal frame in m-dimensional space, where each of those vectors are multiplied by corresponding singular values. So v1 is multiplied by sigma 1 and now points in the direction of u1. So you get a new orthonormal frame that defines, you can think of it as an m-dimensional ellipsoid. So what ends up happening is the singular values, you can think of as defining axis lengths of this ellipsoid. So sigma 1 is the length of a major axis pointing in the direction of u1, the first column of u, then sigma 2 for u2, and so forth. So singular values give you an idea as how a sphere in n-dimensional space is transformed into an ellipsoid in m-dimensional space after multiplication by A. All right. Now, I have more terminology to give about the singular value decomposition. So I can tell you about its many properties. I don't even know how long I've been at this. How long have I been recording? 47 minutes. My God. I wasn't supposed to take that long. Okay. Now, let's see. I've gotten that far. Okay. All right, so first I need to break down U and V by columns. So U has columns, U1, U2, up to UM. These are what called the left singular vectors because A is equal to U sigma V transpose. V has columns V1, V2, up to Vn. So these are the right singular vectors. Okay. So we have this relationship. A times Vi is equal to sigma I Ui. Now, similar to an eigenvalue-eigenvector relationship where eigenvalues and eigenvectors, you multiply an eigenvector by a matrix and you get the eigenvalue times the same vector. But here are different vectors. So A transforms a right singular vector into a left singular vector. Similarly, A transpose Ui is sigma I Vi. So A transpose maps a left singular vector into a right singular vector. And this is for I equal 1 to up to P, which again is the minimum of M and N. So for because if M and N are not equal, you don't have equal size sets of left and right singular vectors. So whichever ones you can have available, these relationships hold. Okay. So by convention, sigma 1 refers to the largest singular value. Sigma 2 is the second largest, and so on. Now, sigma 1 is also referred to as sigma sub max of A, just to make clear you're talking about the largest. And sigma P is referred to as sigma min sometimes, to make clear you're referring to the smallest singular value. Now, with the singular vectors, it's very easy to describe two important subspaces associated with the matrix, because every matrix has a range and a null space. So the range of A, that's a set of all vectors you get in Rn by multiplying by A. So it's like, you know, the range is the output of a function. So if your function is multiplying by A, the ranges are all possible outputs. And that comes from the left singular vectors. So U1, U2, up to UR, where R is the rank of A. So that's the number of linearly independent rows or columns that it can have. R also, it happens to be the number of non-zero singular values. So sigma i's is what I wrote there. Okay, so there's a lot of things. Once you have the singular value decomposition, you can read a lot of properties right off of it. So you look at how many non-zero singular values you have, that's the rank. So that many left singular vectors, the first ones, so 1 to R, that's an orthonormal basis for the range of A. You can also describe the null space of A. Now, the null space of A are vectors that you can multiply by A and get 0. So that would be the span of, in this case, instead of taking the first R of these, it's the rest of them. So you start at V R plus 1, R plus 2, all the way up to Vn. So the rank of, because the rank plus the dimension of a null space, which is also called the nullity, those two numbers have to equal n. So, so you take out the first R right singular vectors, V1 up to Vr, everything else is the null space. So if I multiply A by any one of these vectors, I'm going to get 0. Now, one special case, let's suppose that the matrix is square, so n by n, and invertible. Well, in that case, what's going to happen is the number of non-zero singular values is n. They're all non-zero. The range of A would be all of the left singular vectors, so it would cover a whole space Rn. The null space, you would not have any vectors in here. The null space would be the trivial null space, which consists only of the 0 vector. So it's not a very interesting case, really. Okay. Right. All right. Other properties. So we have that the 2 norm of a matrix A is a sigma 1, the largest singular value. I defined it earlier as the square root of the largest eigenvalue of A transpose A, but this is a simpler definition. Also, the Frobenius norm of A is square root of sum of squares of all the singular values. I guess I can fill in R there for a number of non-zero singular values. So in other words, the 2 norm of A is always less than or equal to the Frobenius norm. In fact, it's going to be strictly less than unless the rank of a matrix is 1. Also, this is something that's meant to be shown in one of the homework problems. The condition number of A in the 2 norm set. So that's the 2 norm of A times the 2 norm of A inverse is sigma 1, so sigma max, also known as sigma 1, over sigma min. For a case where A is invertible, so in that case, the smallest singular value of A, so that'd be sigma n, is non-zero. But suppose the matrix is not square, or otherwise doesn't have an inverse. Then this ratio, well, even though you can't write A inverse, this ratio of largest to smallest singular values can still give some useful information about the sensitivity of a matrix, like how close it is to a singular matrix. Suppose you have a matrix with more rows than columns. So the super columns are all linearly independent. If this ratio of sigma max to sigma min is large, that means those columns, while linearly independent, are close to being linearly dependent. So A is close to a singular matrix. Okay. So this is a particularly convenient formula for the condition number of A. Mostly in a theoretical setting, because individual singular values are generally not easy to compute, unfortunately. Because really the condition number is not easy to compute in any norm because you're dealing with some norm of the inverse, and you don't want to go to the trouble of computing the inverse. Okay. Now, I want to talk about a different sort of least squares problem than I've been talking about previously. So an underdetermined system of linear equations, AX equals B. So this time M is less than N. So now in a case where M is greater than N, you generally have a situation where there is no exact solution to AX equals B, and you try to minimize the norm of B minus AX. In the case where M is less than N, and where as long as B is in the is in the range of A, you can get a solution, an exact solution, but the trouble is now you have infinitely many solutions. So you might want to have some criteria for picking out one solution in particular. Okay, so I can give you an idea of how you can do that. Okay. So I'm going to assume that the rank of A is equal to R. Now, I'm not going to make any assumptions about R. We know R is less than or equal to the minimum of M and N. And really what I'm going to tell you can be useful for not just underdetermined problems, but any AX equals B problem where you have the rank of R. So, and the most interesting case is when R is strictly less than both M and N. Because that's a situation where you can have infinitely many solutions. And you need to pick for one's a right one in a certain sense. So what I'm going to do is examine B minus AX 2 norm using the singular value decomposition. So first I'm going to replace A by its SVD. And I'll work with a 2 norm squared for convenience. Use sigma B transpose X. Okay. Now, I can multiply this expression by any orthogonal matrix and it will not change the 2 norm. So I'm going to multiply by U transpose to cancel out the U. And then I'm going to define some symbols here. I'm going to let C, the vector C, be equal to U transpose B. And I'm going to let Y be equal to V transpose X. So now I have a true norm of C minus sigma Y. So I went from B minus AX to C minus sigma Y. Now, it may seem like I haven't done anything useful, except for one thing. Sigma is a diagonal matrix. So it's a lot easier to write out what this is. I can write it component by component. So C is a vector in m-dimensional space, and so is sigma Y. So what I get is C1, first component of C, minus the first component of this. So that's just going to be sigma 1, Y1. And this is a Euclidean length, so it's a sum of squares. And then I have C2 minus sigma 2, Y2 squared, and so forth. And I'll keep going all the way to R. Okay. Now what happens after that, I only have R non-zero singular values. So any other entries, like in the subsequent columns of sigma, are going to be all 0. So I'll be multiplying I've used components y1, y2 up to yr. Any other components in y up to n are going to be all 0. So I won't get anything from this term anymore. I will have components of c. cr plus 1 squared, and so forth, all the way up to cm squared. So that's the two norm of c minus sigma y. Now, I want to make this as small as possible. Now, these are not unknowns. They're known because they come from U transpose B. I cannot affect those in any way, so I'm stuck with them. The only way to minimize this is to make each of these terms in parentheses equal to 0. So, because the only thing I can affect are the only unknowns I have are in y. So I can set yi to make this 0. I can set each one of these equal to 0 and solve for yi. So it's going to be ci divided by sigma I. And those sigmas are all non-zero, so I can do that. So that'll give me the first r components of y. The other ones, however I set them at all, it's not going to affect this. So I'll talk later about how I might set them. But once I have y filled in, then I can take this equation and solve it for x. I can multiply both sides by, on the left by v. So x, my solution x, is going to be vy. So this is what I can do. Once I have a singular value decomposition, and I compute the vector c, u transpose b, I just do this. I can set these components of y for 1 to r, and then whatever I have in y, I multiply by x, and I'm done. I've solved my least squares problem. Okay. Now, I want to relate this to, now, like I said, what I've done here does not require these assumptions of being underdetermined. It works regardless of the relationship between m and n and r. For example, the problem I've been covering in this chapter, the full rank least squares problem, in that case, r is equal to n. So, and y is an n vector. So what ends up happening is this right here, this formula sets all the components of y. I don't have any components left over, which makes sense because we've already established that for a full rank least squares problem, there's a unique solution. There's no flexibility whatsoever. And then, so this is how the same problem will be solved using the SVD instead of the normal equations or the QR factorization. But the SVD is just as expensive to compute, really, I think more expensive. Actually, it is more expensive. than those other approaches. But what it reveals about least squares problems, if you are able to compute it, is can be quite helpful. Okay, so if I do have components of y that are not set by this, like for the case where r is strictly less than both m and n, so in other words, that's the rank deficient least squares problem, I have some flexibility there. So what can I do? I can set the rest of those components, y r plus 1, r plus 2, up to yn equal to 0 if I want, for what is called the minimum norm solution. Because those components of y are uniquely determined. If I set all the rest equal to 0, then that means that the 2 norm of x is made as small as possible. Now, why does that matter? So this is a very crude example of what is called regularization. So if you're trying to solve a certain equation where there are infinitely many solutions possible, you might want a solution like some data fitting problems or like image or signal processing problems can have solutions that are extremely oscillatory. They have a lot of noise in them. So what happens is you may have quite a few components in your solution that are adding this noise. So if you try to make the solution smaller in some sense, so have certain components not present, then depending on how you go about it, that can lead to a solution with a solution with less data in it. It's therefore less likely to have this spurious noise or oscillations or what have you. For example, if this solution as I've defined it here is something that lives in frequency space or Fourier space, these might correspond to high frequency components and these are low frequency components. If I set the high frequency components to 0, then the overall solution is smoother, or it's also said to be regular, thus the term regularization. So there are a lot of problems like this where you're trying to minimize something, but you have some leeway. So a common way to exploit that leeway is to make minimize some other property of a solution. For example, the 2 norm, or maybe not 2 norm of x, but maybe the 2 norm of something times x, so that the solution is well behaved in some sense. So that's a very common practice in various fields like image processing, data analysis, etc. Okay, now, how much of these notes have I gotten through? Unfortunately, they're all out of order. Okay, we did that. Okay, I have this example. I might do that. Okay, covered that. Okay, I actually do have. All right. Let me make sure I'm not missing anything. Okay. Unfortunately, I need to make this 2 lectures. One on the SVD, because I'm already at 1 hour and 9 minutes. One on the SVD and the other on least squares of linear constraints. So we can come back tomorrow and do that one. Ugh. Not fun. Okay. Now, there's another way to look at this solution to this least squares problem that I described. Because as I mentioned earlier, x is equal to v times y. Now, but how did I define y? Y is obtained by taking the components of c and dividing them by the singular values as much as I could, all the non-zero singular values, and then like setting the rest equal to 0. So I can write down matrix vector form. So what happened was, I put my vector C1 down to CR, and then CR plus 1 down to CN. Okay, so what happened here? For first R values, I multiplied them by the reciprocals of the singular values. And then everything else, these other components below this line, they're all multiplied by 0. I want the minimum norm least square solution. So now we have this matrix that is related to sigma. So I'll write out what sigma is. So here the matrix is, well, actually I haven't specified anything about the size and dimensions of it, but I have sigma 1, sigma 2, sigma r. Then if I have any other diagonal entries below that, they would be 0. Okay. So you can almost think of this matrix as kind of like an inverse, because at least where you have non-zero diagonal entries, I have reciprocals over here. It's just that here I have zeros I can't take reciprocal of, so I just say, let's put zeros in here. So I can't call that the inverse. It's not the inverse. It's a pseudo-inverse. So I'm going to call it sigma plus, and then times c. All right. Now, what is c? C was defined earlier to be U transpose V. So this, now remember, the singular value decomposition is U sigma V transpose. Now here everything's in reverse order. V sigma plus U transpose. So I'm going to call this A plus B. And A plus here is called the pseudo inverse of A. It's also called the Moore-Penrose inverse, or generalized inverse. Well, I'll stick with the term pseudo-inverse. Now, in the case where A is a square invertible matrix, the pseudo-inverse coincides with the inverse. But in the case where A does not have an inverse to speak of, this is as close as you're going to get. And so it's obtained by taking the reciprocals of any non-zero singular values. So to compare, the square invertible case, you have a problem, ax equals b. There's a unique solution. X is equal to A inverse B. If you do not have that, then the solution of this problem, where you're trying to minimize the 2 norm of a residual vector b minus ax, and you're also trying to minimize the 2 norm of x. It would be the pseudo-inverse times b. Oops. Okay. All right. So this vector x, a pseudo-inverse times b, minimizes both of these. Okay. Now, there are cases where one of these may not apply. or be trivial. For example, suppose B is in the range of A. Then B minus AX can be made 0. But depending on the rank of A, you might have infinitely many solutions that in this criteria will pick out the minimum among those infinitely many solutions. Another possibility is that if the rank of A is equal to n, then you're only going to have a unique solution. So you try to find a minimum of just this. And because it's going to be a unique solution, that criterion is automatically satisfied because there's only one vector to consider. So you're trying to find x that satisfies both of these. So in sometimes in one case or the other, one of these is naturally eliminated and you're focusing on the other one. But in the most general case, you're trying to find this vector that will satisfy both. Okay, like in the case where you have infinitely many solutions, for example. Okay, so this is not the only way to obtain the pseudo-inverse. There is another approach, actually in section 4.3 of the book, which I didn't bother covering, that defines it in terms of the QR factorization, but it's finding the SVD more interesting. And we're going to be using the SVD more during the semester anyway. Okay, now, so now I want to get to another very important application of the SVD. And then finally, that'll be all I have to say about this. So sorry I've had so much to say, but then again, considering the importance of my advisor to the SVD, it was bound to happen. All right, so now I want to talk about low rank approximation. Using the SVD. Now, I'm going to break down U sigma and V. So U, I'll break down into U1 and U2. So U1 has R columns, where R is a rank, and all the other columns are in U2. I'll break down V similarly. So R columns in V1, n minus R columns in V2. And then sigma will break down into sigma 1, so that's an R by R matrix that has all the non-zero singular values, so it's invertible. And then all other blocks will be 0, because sigma is a diagonal matrix, and sigma 1 contains all of the non-zero diagonal entries. So I can write out A, which is U sigma V transpose, and I'll fill in my block structure. I have U1, U2, and then I have sigma, and then V transpose. I got to transpose this, so I'll have V1 transpose, V2 transpose stacked on top of each other. Okay, so now what I can do is I can carry out this matrix product. So what will happen is, okay, so I'm going to get U1, U2. So I carry out this product, sigma 1, V1 transpose plus 0, 0, 0. So I'm going to get sigma 1, V1 transpose, and then 0. So now I'll multiply that by that plus that by that. So what I get is U1 sigma 1, V1 transpose. So it looks the same, except this is called the thin SVD, similar to the thin or economy size QR factorization, where you're just getting all the things you actually need, a minimum amount to construct A. So U1 is M by R, sigma 1 is r times r and invertible. V1 is n by r, but it's transposed. So V1 transpose would be r by n. Okay. So I can write this out in terms of the appropriate left and right singular vectors of A and the first r singular values. So I can write it out as a sum from 1 to r, ui sigma I vi transpose. So now the sigma I is a number. I can put that anywhere in here, but I just want to preserve the order of how things are written here. So this is called the SVD expansion. So if the rank of A is r, I can express A as r terms consisting of the first r left and right singular vectors of A and the first r singular values, which are the only ones that are non-zero. So really, I would have more terms in here since those terms are zero, so why include them? Okay. Now I want to point out before I continue, let's suppose that r has a pretty low rank, like r is much less than m or n. Well, A has m times n entries in total. Whereas, what's my storage if I just only store these singular vectors and singular values? Well, I have m entries in each of these vectors, n entries in each of these vectors, and then these are numbers. So my storage is m times n in this case, but in this case I have r for rank, so that's how many terms I have. Each term requires m entries for this vector, n entries for this vector, and then 1 for this number. So m plus n plus 1. So let's suppose that r is quite small compared to m or n, then this storage could be a lot less. So if you're able to go to trouble for computing the SVD, which actually may be quite reasonable in the case where A is low rank, you may be able to get those singular values, singular vectors faster than you could otherwise, then that's good for like image processing, image or signal compression, that you are representing a matrix using a lot less data than in its original form. So you're able to store it in a compressed form using the SVD. Okay. Now, so that's one benefit of the SVD expansion. That's good for data compression. But now suppose we might determine that some of these terms, even among these R, we don't need. For example, suppose some of these singular values, like up to like sigma r, or the smallest singular values, suppose they are quite small compared to the largest ones. Then perhaps we can not bother with those terms. Perhaps we can toss them out and compress representation of A even more. So this is where I get to low rank approximation. So I'm going to let K be strictly less than R. Otherwise, there wouldn't be much point. So the best rank K approximation of A is matrix I'll call A sub K. All it is it's that same expansion, except I cut it off after K terms. So I get sigma I, ui, vi transpose. Notice these are outer products, which you've seen before. Okay. Now, so what I could do is I could actually say what the error is going to be in this approximation in a two-norm sense. So A minus AK, two-norm. Well, A is the whole expansion, all R terms. AK is just the first k terms. So if I subtract them, terms corresponding from 1 to k are going to cancel. So what's left is terms k plus 1 up to r. Well, this also is a singular value decomposition of a matrix. And these are left and right singular values that came from A. It's just different singular values. But first, k singular values are 0. And then we have the other non-zero singular values in this sum. Well, what's the largest one of those? Well, remember, the singular values are ordered from largest to smallest. So the largest singular value of this matrix would be sigma k plus 1. So if you choose the rank k approximation, then the error in that approximation in a two-norm sense is the next singular value, sigma k plus 1. So if you have a singular values, then you know what the error is going to be in that rank k approximation, just by inspecting singular values. You might be looking at singular values and think, oh, here's a singular value that is extremely small, like maybe it's 10 to the minus 8 or something. And any other ones will be smaller than that. So you decide, okay, I'm just going to cut it off there, and I'll still have a really accurate approximation, at least the absolute error in the two-norm sense. Similarly, using the fact that the Frobenius norm of a matrix is a square root of sum of squares of all the singular values, I can write down the error in this rank k approximation in the Frobenius norm sense. So that would be the square root of sum of squares of all the singular values starting from k plus 1 up to r. So you could use that criterion as well to get an idea as to, like maybe you're trying to choose k in such a way that the error is below a certain threshold. So you can choose that threshold to be either based on the 2 norm or the Frobenius norm. So low rank approximation can be very helpful, again, for data compression. For example, if I take an image, so in fact, there's functions in MATLAB that you can use for this. I can take an image file, like a JPEG, so something took using your phone, and so you have the image file, the JPEG file, and you can use the function imread to read it into MATLAB, and then if the image is m by n pixels, the structure that you get is a three-dimensional array that's m by n by 3. You have 3 channels for RGB, red, green, blue. So you can take one of those slices, now you have the m by n matrix. So you can take the SVD of that matrix and drop some of these terms in the SVD expansion. What often happens with images, if you just take any random image, the singular values tend to tail off quite quickly. You have certain terms of importance, and then the singular values at some point will plunge towards 0. So you could take however many terms you want, k terms, and zero out the rest of them. And then you can reconstruct that matrix with those terms removed. That's going to be an approximation of the original. And you can display the image. And if you've chosen enough terms, then the images will look very similar. And so when I taught COS 702, a data analysis class several years ago, that was actually one of the assignments of using the SVD to achieve compression by cutting out a certain number of terms. And you can see that as long as you retain enough terms, you wouldn't visually, you could not really tell the difference between the images. Okay. Now, so a very simple example of a low rank approximation. Okay. So the matrix I'm going to use here is, and it's in the book, but anyway. Oh, wait. Okay. Yeah, this is the one I want. So let's suppose my original matrix 11, 19, 11, 9, 21, 9. by 3 matrix, and U sigma V transpose. I won't write out U and V. They are written out in the book. Sigma, the singular values are roughly, I'll just keep 1 decimal place, 2 decimal places, 42.43, 2.45, and 0. So I actually made it as a singular matrix. So the rank is a number of non-zero singular values, which is only 2. If I want the rank 2 approximation of A, okay. Oh. Well, actually, no, not rank 2. If I take rank 2, it would not be an approximation. I want a low rank approximation, so that would be A1. Would be this singular value, 42.43, times the first singular vector times the transpose, so the first left singular vector times the transpose of the first right singular vector. So this is a rank 1 matrix, and so that matrix turns out to be 10, 10, 10, 20, 20, 20, 10, 10, 10. And you can tell it's a rank 1 matrix because each, well, in a rank 1 matrix, each row is a multiple of all other rows. Each column is a multiple of all other columns. Here we have all the rows being the same. So that's trivially true. But if you notice, if you look at the entries, these entries average out to be 10, these entries average out to be 20, and these entries average out to be 10. So you kind of tell it's a semi-decent approximation. So the error in a 2-norm sense is going to be the size of this singular value, 2.45, which is sigma 2. Now that is the absolute error. So it's a 2-norm of A minus A1. For relative error, is the 2-norm of A minus A1 divided by the 2-norm of A. So that would be this singular value, 2.45, divided by the 2-norm of A, which is the largest singular value, 42.43. And that's roughly 0.06. So in other words, the error in this rank 1 approximation is about 6%. So not bad, considering it's just a rank 1 approximation. You generally can't expect much from rank 1. So this good idea is how we make low rank approximations, that we can see that the SVD expansion for this matrix, because there are only 2 non-zero singular values, would only have 2 terms. And then if we want to approximate, we'll just toss one of those terms out. So this term was not really all that negligible, so that's why the absolute error was kind of large, but at least in a relative sense, because of the difference between these singular values, it's, in a relative sense, this approximation is not so bad. Okay, so that's a rundown of the SVD, except for how to compute it. That's something we'll get to closer to the end of the semester. Okay, so if you haven't done the quiz yet, at least you can answer the SVD questions about it, or if you tried to quiz and got those questions wrong, hopefully this will help you get them right. So, all right, I'm going to end this and upload it, and then decide if I want to, we'll see, it's, oh, my computer says it's 3 o'clock, but it's actually 5 o'clock because I forgot to switch it back to Central Time, dang it. So I'll just decide if I want to stick around, but this video file is already large enough for sure.